Okay, so the goal today is to continue our study of Dirichlet L functions and primes in arithmetic progression. So we're trying to generalize the Riemann zeta function zeta of s. And so we talked about how zeta of s is the sum and goes from 1 to infinity of 1 over n to ds, and it's also the same as the product over primes of 1 minus p to the minus s inverse. So the Euler product is an extremely important part of the Riemann zeta function, and this is because of unique factorization. We talked about how we can form characters chi from z mod mz star to the complex numbers. Well, initially we define it not just to the complex numbers, but to the complex numbers of absolute value 1. And we're only defining it on the integers that are relatively prime to m, and we set it to be 0 everywhere else. Well, this allows us to extend it, and then rather than looking at it as a function from z mod mz star, we can look at it as a function from z to the complex numbers. And it's almost always to a number of absolute value 1. Every now and then, we have it goes to a number that's 0. And these Dirichlet characters have a lot of very nice properties. So the big ones are the orthogonality relations. So where else in this semester have we seen orthogonality?
Fourier transforms.
Fourier transforms, when we looked at the basis of sines and cosines. So we have this infinite dimensional space, and we want to represent things so much in sine, so much in cosine, so much in sine 2x, so much in cosine 2x. Or instead of doing sines and cosines, it's a little bit more natural sometimes to use exponentials. E to the I in theta, e to the 2 pi I in theta, depending on whether or not you're a physicist, a mathematician, economist, you might use slightly different normalizations. Doesn't really make much of a difference. The main thing is something in terms of sines and cosines, something in terms of exponentials. What's nice about orthogonality is you can represent it very cleanly in terms of a combination, and you often get relations such as the norm is the sum of the squares, square roots, something like that. So here the orthogonality goes in two different ways. Let's look at the sum of chi of n. So I have two possible things I could sum over. What could I sum over?
N.
I could sum over n,
Or
or
you can sum
I could sum over the characters. So I should get something good in both ways. So if I sum n mod m, I actually don't have to worry about wanting to sum over all n mod m or just the n that are relatively prime, because if it's not relatively prime, it's just 0. How many elements do I have?
phi or totient of.
So I have phi of m ones that are legitimately playing a role here. Right? I have m minus 1 numbers if I'm looking at all the residue classes, but a bunch of them just always give me 0. So if I'm trying to figure out how large could this sum be, it's very natural to divide by the number of things in play. And so if I divide by 1 over phi of m, this is then a really good quantity. So this is the average value over the things that could contribute. Now each of these numbers is at most 1, so the average value of this is at most 1. In fact, the value of this is at most 1. But we could have some cancellation. And this is the whole reason why Dirichlet characters play an important role, is that typically there is cancellation. There's one situation when you do not expect to have cancellation. What's that situation? So what value of n will not have cancellation?
0.
Well, if I put in 0, chi of 0 is always 0. So it's not 0, it's the only other number.
1.
It's 1. Right? We have a group homomorphism. Chi of A and B is chi of A, chi of B. So this tells us chi of 1 is chi of 1 times chi of 1. Chi of 1 is either 0 or 1. And if chi of 1 is 0, well then we've just defined a mapping that sends everything to 0. A map that sends everything to 0 is not going to give us any useful information. Right? I wonder what that map's going to do to this. It's going to send it to 0. What's it going to do? It's going to send that to 0. No useful information at all if it just sends everything to 0. So what we want to do is we want to set chi of 1 equal to 1. So this sum is going to be 1 if n is congruent to 1 mod m and 0 otherwise. And then the other thing we could look at is we could look at a sum of all captors chi mod m. And it turns out there's also phi m of them. And we could ask what's going on here. And so now, if n does not equal 1, what do you think we would get? Oh, wait a minute. Okay, here we sum it all. Now I want to sum over all the characters. Okay. So wait a minute, I think I might have just written this the wrong way. Right, sorry, I wrote this the wrong way. My apologies. This is the one I want to do over, sorry, chi mod. No. It's fine. I'll do it this way. Okay. So we'll do just chi mod n. Right, but I'm saying if I say that n is congruent to 1 mod n, if I'm summing over n, I'm mixing up the two parts over here, right? So this is, we can either keep this over here or we can sum over the characters. So sum over the characters chi mod m. And so now, if n equals 1, every time I put in a character, I get 1. Because we always send 1 to 1. It's a group homomorphism. I just wrote the wrong subscript over here. You know, if I'm summing over n, I can't have n on the right-hand side. Now over here, this is the one where I want to sum over n mod m. And now it's going to depend on what character I put in. So if I put in the trivial character sends everything that it can to 1. It doesn't send everything to 1, it just sends everything relatively primed to m to 1. So if I put in the trivial character, I get 1 every time. I have phi m of them, I divide by phi of m, I get 1 if chi is the trivial character, and we denote the trivial character by chi naught. And then we get 0 otherwise. Okay, so the proof of this fact is fairly nice. I think I do one in the book. Let's do one of them here. So let's study the sum of chi mod m 1 over phi of m chi of m. So chi is ranging over all the characters. So I'm not going to go through all the details, but it turns out we have a group here. And let's call this sum S of n. So S for sum, and the n to remind us that it's depending on potentially the n we have. And so what I want to do is I want to look at a nice tweak of this. And the following is a really common idea that's used all the time. We want to change the summation. And so the question is, what is the best way to change the summation? So we're going to change summation as follows. Fix a character chi tittle. As chi runs over all characters, so does chi tilde times chi. So I believe everybody in this class except myself has taken abstract algebra. So you've all seen finite groups. And so here I have a finite group, and I'm multiplying by one element. So it has to range over all things. If I ever had chi tilde chi 1 equals chi tilde chi 2, well, I can cancel by chi tilde inverse on both sides and get chi 1 equals chi 2. So this will range over all possible characters. So this is the same, Sn is the same as the sum 1 over phi of m chi tilde chi mod m. So I'll leave it like this. The sum of all chi mod m of chi tilde chi of n. Because as chi ranges over all characters mod m, so does chi tilde chi. But what's chi tilde times chi of n? That's chi tilde of n, chi of n. So we can pull a chi tilde n outside, and we get Sn is 1 over phi of m, sum chi mod m, chi of n, and I'm going to pull out a chi of n tilde. Well, what's the sum over here? Sn. So we have the wonderful situation Sn equals Sn times chi tilde n. What can you deduce?
Sn equals 1 if chi tilde doesn't equal 0.
Good. So if chi tilde of n is not 0,
then we must set Sn equals 1. Or sorry, Sn equals 0.
so we want to say Sn equals 0 if chi tilde of n does not equal 0. That's not enough. Because remember, we're going to choose n to be relatively prime to m. So this is not going to be 0.
Well, we can choose. Actually, never mind.
Oh, if it doesn't equal 1.
It doesn't equal 1. If this equals 1, we have no information. Well, if this equals 1, what does that mean? Choose a different character. And if that character equals 1,
Choose a different character.
unless there's no character you can choose, there's only one way you can't have a character that doesn't send it to 1. If n equals 1. If n equals 1, everything sends it to 1.
If n or
If n. If n is 1, every character will send n to 1.
also if n is 1, right? Or no.
Well, m is fixed, like m is the modulus. So if we're in the situation that n equals 1, there's no way I can choose a chi tilde such that chi tilde of n does not equal 1. Chi tilde of n will always equal 1. But if n does not equal 1, I can find a character. So the idea is if chi tilde of n is always 1, it forces n to be congruent to 1 mod m. Sum is easy. Right? We're just summing 1 phi of m times. And then it gives us that Sn is equal to 1. Else, there exists a chi tilde such that chi tilde of n does not equal 1. And then that's going to force Sn to be 0. So this is where we get the orthogonality. That when you look at these complete sums, the only time the complete sums don't average to 0 is if you happen to be in a situation where you're always summing 1. If you always sum 1, you should not expect to get 0. You should not expect to get any cancellation. So if you think about it, the orthogonality relations, we're just primitively swiveling today, the orthogonality relations is the best you could expect. You can't expect better than this because if you plug in n equals 1, you've got to get back 1 every single time. But if you put in anything else, it's going to average out. And this is the great advantage. When you look at the partial sums of the coefficients, so now what that's doing is that's fixing a character and looking at sums like this. If we take the trivial character, I'm not going to bother doing the proof, I'll leave that to you. If we take the trivial character, what are we going to get? We're going to get basically 1 every single time that n is relatively prime to m. We're going to get something that's very large. If we take anything other than the trivial character, we're going to get massive cancellation. One easy way to see this is we talked about how if m was a prime number, we could write down everything explicitly in terms of the exponential function. And we could write down what was happening to a generator, and then we just have exponential sums. What formula do we use to analyze exponential sums? Geometric series. So you would just apply the geometric series, and then you would get the cancellation. This allows you to analytically continue Dirichlet L functions with great ease. And the reason is you can now play these partial summation games. And you have the sum of chi n over n to the s. Well, if we just had the sum of 1 over n to the s, if we tried to do partial summation, the problem is the sum of the numerator is going to just get too large. Partial summation, did we talk about that in this class? I thought we talked a little bit about partial summation. It's the analog of integration by parts.
It was in the book.
It's
I
in the
don't think
book,
we
I don't
ever.
think we
did
Okay,
it.
okay. Alright, so I will give you some stuff to read about partial summation. It's equivalent to integration by parts. And so just formally, as a quick heuristic, you know, the integral of u dv is uv ab minus the integral from ab of v du. What you get with partial summation is if you have something like the sum of an h of n, where maybe h is a nice differentiable function, and you have n goes from, say, 1 to x. This is like a of x, h of x, minus the integral from 1 to x of a of u, h prime of u, du. So this is a discrete version of integration by parts. There may be a boundary term here when n equals 1. I'm not going to worry about it because I'll just assume maybe a1 is 0.
Do you mean the sum from 1 to x?
I'm sorry?
Do you mean in the second half? Do you mean the sum from 1 to x?
Which one over here?
Yeah.
No, this is the power of partial summation. And here, a of u is the sum n less than equal to u of a sub n. So when you unwind what this is, it's going to be constant in regions and then have bumps up. And now when you integrate over here, well, h prime is then going to become h of u in places where it's constant, and it's going to basically become h of n, and that's going to reduce to this. So partial summation is a discrete version of integration by parts. If you look at the sum a of u, if you take the Riemann zeta function, how big is the a of u going to be for the Riemann zeta function? So for the Riemann zeta function, a of n is 1, h of n is 1 over n to the s. So how large will a of n be? Or how large will a of u be? It's going to be of size u. And over here, I have 1 over n to the s. I'll have 1 over n to the s minus plus 1. So I would get over here for the Riemann zeta function, this is going to look like u. This is going to look like 1 over, I don't care about the s, u to the s plus 1. The plus 1's cancel. This is going to blow up as s goes down to 1. And this is why the Riemann zeta function can't be continued so easily. But if I look at the Dirichlet L functions, what do you know about a of u? How big is a of u? It's at most phi of n. It's bounded. So now, if we do Dirichlet L functions, this becomes a chi of n. And now this is of size phi of n. And now we have extra decay down here. And you basically get very cheaply the analytic continuation of Dirichlet L functions. So it's not hard to continue the Dirichlet L functions because you have cancellation. So in general, the more cancellation you find, the more you can do. Okay. Any questions on the basics of Dirichlet L functions? Okay, so what would Dirichlet L functions introduce to study?
Or
We're not saying
primes
primes and arithmetic progressions. So primes and arithmetic progressions, this is a beautiful segue into the circle method. So I am choosing a strange order of the book. I'm trying to focus on a unified theme, applications of Fourier analysis. And so I want to do the Fourier analysis first. We would really have that at our disposal for this chapter. But primes in arithmetic progressions. The following is one of the strangest ideas I've ever seen in mathematics. It works, so it deserves respect. Let's say I want the following. I know I ask a lot of you. I apologize for asking so much of you. All I want is one prime congruent to A mod M. That's all I want. I want 1 prime P congruent to A mod M. All right. What must be true in order for me not to be an unreasonable professor?
M is greater than 2.
No, I mean, if M is less than 2, it's much easier. Right. Then I would have a very different reputation on FactTrack. What do I need in order for this to be a reasonable search?
Relatively prime.
Yeah.
And
P and M.
Well,
no, that's...
So P's what we're going
that's
for.
just-
Do I need any conditions on this to be a reasonable professor? So if P is, A is relatively prime to M. So but what if A and M share a prime factor? Is it always possible to find a prime congruent to A mod M? Or can you give me an example where you can't find a prime congruent to A mod M? So if there's going to be an example, look composites.
Do you mean other than A?
Well, if A works, that's an example. I didn't say find a good example. I just said find a prime. If I'm trying to find primes congruent to 3 mod 17, here's 3.
you're like 4 mod 8.
Okay,
Yeah,
so
right.
4 mod 8.
Yeah.
So, for example, no P are congruent to 4 mod 8.
Yeah, 2 mod 4 would work except for
2's a prime.
Okay, so it is unreasonable for me to expect you to be able to do this if A and M share a common factor and A is not prime. So clearly, a necessary condition is A and M equals 1 unless A is prime. And of course, if A is prime, it's boring. So you should always say, find a prime other than A. Otherwise, we'll assume A and M is relatively prime. What's interesting is this is sufficient. So that's not immediately clear. That just assuming the bare minimum that you need to make the problem interesting is all you need to get to a solution. But there will always be a prime that is congruent to A mod M, so long as A and M are relatively prime. This is the best possible result you could expect in terms of existence. The proof is phenomenal. So the general case is the following. There are infinitely many P congruent to A mod M, and thus there is a P congruent to A mod M. Have you ever heard the expression killing an ant with an elephant gun? This is several orders of magnitude from that. This is you're bringing in atomic weapons. This is enormous overkill. How do you prove one exists? Oh, I proved that there's infinitely many, and if there's infinitely many, there must be at least one. Okay? Amazingly, this is one of the best techniques we have for proving theorems. To prove existence, one of the ways you prove something exists is you show it happens so many different ways, it must happen at least once. We will see this all the time in the circle method. The way we prove that there are solutions to certain equations is we count how many solutions there are. And we get a really good estimate for how many solutions there are. And if that estimate is positive, there must be at least one solution. Now, there are times when you can actually prove these things elementarily. So remember Euclid? How did Euclid tell us that there were infinitely many primes? What did Euclid do?
Assumed otherwise.
Assumed otherwise and...
Showed that there has to be one that we haven't counted.
So what did he do?
Multiply them all
Multiply them
together.
So you multiply them all together, B1, Pn, and you add 1. Well, what's the natural thing to try for Dirichlet? So we want primes in arithmetic progression. What should we try?
Assume there's finitely many.
Assume there's finally many, and
Take the product.
take the product. So maybe we'll look at P kind of go into 1 mod 4, and primes kind of go into 3 mod 4. And what we can do is we can multiply them all together, P1, Pm, and add 1. What is this going to be congruent to modulo 4?
2.
Is there, so that might be bad. And I need to fix it. What could I multiply by to get this to have the right congruence value?
2.
Twice the product.
Not, I don't have to multiply the whole thing.
Oh, yeah, twice P1 through n plus 1. What you said?
Yeah.
I want to do a little bit more than that. I want to do twice what you're saying. I want to multiply by 4.
Oh, to get it, yeah, back to the same. Yeah.
Although, because unfortunately 2 is not congruent to 1 mod 4, so 2 is not on the list. Everything in the list is odd. If I multiply by 4, this is now of the form, 4m plus 1. On this side, I can look at 4, I'll call it P1 tilde, Pm tilde, plus
3.
plus 3. Let's assume there are only finitely many primes congruent to 1 mod 4. Here's a list of all of them. Could all the primes that divide this number be congruent to 3 mod 4?
Divide that sum right there?
Yeah.
Yeah.
So if you're congruent to 3 mod 4, and you multiply yourself by something else that's congruent to 3 mod 4, what are you congruent to mod 4?
1.
1. So unfortunately, if 2 primes divide and 3 mod 4, their product is 1 mod 4. So when we know that this number is composite or prime, if it's prime, great, we win, but if it's composite, what if it is divisible by just primes on our list and 2 primes that are 3 mod 4? Unfortunately, in that case, we would not be able to conclude that this is a new prime. What about over here? Is it possible that this could only be divisible by primes that are 1 mod 4?
No.
It's got to be divisible by at least 1 prime 3 mod 4. At least one new prime that is 3 mod 4 divides. Therefore, infinitely many. Therefore, back to work. So we can elementarily prove in some cases that there are infinitely many primes congruent to A mod B. Unfortunately, these elementary arguments do not work for general A and M. Sorry, I sometimes move M to B for obvious reasons. It's interesting to see how far you can push these. One of my colleagues, Ramurti, has a nice paper. I'll try to find that. Question?
I mean, what if 3 is the one? Oh, why is it at least one new prime?
Because I will assume that I've included 3 over here. Oh, have we made this number multiple of 3?
Yeah. I mean, if the first one's 3, if it includes 3. You could just say you don't include 3 in your list.
Okay, so I think we might want to do that. So let's check. If we don't include 3 in our list, 3 divides this, 3 does not divide that.
But what if then 3 is the new one that you get?
Can't be, because 3 divides 3.
Well, the new prime.
No, but I'm saying, let's assume none of these
Yeah.
are 3. If none of these are 3, 3 divides 3, but 3 does not divide this. So you're absolutely right. So P1 tilde equals, what's the first prime coming into 3 mod 4 that's not 3? 7. So our product is non-empty. So do not include 3. Excellent. Remember to email me. Do not include 3. If we do include 3, we have to be a little bit careful. One way we could probably get around it is play some games, maybe put in some extra factors of 3 to balance things out. Maybe put another 3 here and a 3 there. But I think the safest thing is just not to include 3. What's really going on here is that 3 is -1, not 4. And how many of you have heard of quadratic residues and quadratic non-residues? Alright, this is a bit of a digression, and since no one has heard of it, since this wasn't done in your algebra classes, I'm not going to go into that. This is discussed a little bit in chapter 1, but there's a reason behind this bias. It all comes down to when can you write your number as a square mod m. So we say your quadratic residue if we can write you as x squared. We say you're a non-residue if we can't. And of course there's one number that causes a little bit of trouble. Which number do you not really want to consider a square?
1.
No, 1's fine, 1's good. 0, right? So we'll talk about like the non-zero quadratic residues. And so what's going on here is the fact that -1 times -1 is 1. That's actually helping us. Alright, so this is a brief introduction to the basics of Dirichlet functions. We've got about 5 minutes left. I'm trying to think if it's worth starting the next item. Let's just go through, I guess, just one of the expansions. So we'll have the expansion in the bank for next time. So we will not get to the 5-step proof of the infinitude of primes in arithmetic progression. We're making progress. It was 7 steps to do the Riemann zeta function. It's 5 steps here. The reason it's only 5 steps and not 7 steps is we're glossing over an enormous technical detail and we're just burying it in 5. And so 5 is really the major result and it's the source of all the difficulty. So I don't know if this will survive, but I'll like save here. I'll keep that until Wednesday. So the main idea is the following. So we have L S chi is the sum of n goes from 1 to infinity of chi of n over n to the s. It's the product over p of 1 minus chi of p over p to the s inverse. So as soon as you see this, what is your thought? What is it that you want to do? Log. You want to take a logarithm. Right? We understand products by taking logs. Now, of course, why do we take logarithms?
Compare products to sum.
We already have a sum. Why the hell would you want to take a logarithm?
Logarithmic derivative?
We could take a logarithmic derivative, and that's non-trivial. Because a logarithmic derivative will now give us something that we can use complex analysis on. So the proof I'm eventually going to show you will not use the high-level complex analysis and contour integration. But a logarithmic derivative is different than just a logarithm. It's a logarithm with a purpose. And the purpose is to integrate, okay? So there is a reason to do a logarithmic derivative. If we just take a logarithm, though, why would we want to take a logarithm to convert a product to a sum when we already have a sum? We already have a sum.
The other sum might be nicer.
The other sum might be nicer. In fact, the other sum is nicer. And again, you're supposed to be very careful with these value judgments. So, nicer might be the wrong word to use. The other sum is more useful for the purposes at hand. What are the purposes at hand? To look at primes in arithmetic progression. Well, if you want to study primes in arithmetic progression, you want to look at
Primes.
not integers. And so there the Euler product would be useful. So if we take the log of L S chi, that's then going to become negative sum over p, the log of 1 minus chi of p to the minus s. And in fact, we could then stop and say that the log of ls chi is minus the sum over p, the sum k goes from 1 to infinity. The log of 1 minus u is negative u minus u squared over 2 minus u cubed over 3. The minus signs cancel, and we'll get a chi of p over k p to the ks. We could also take the logarithmic derivative, and if we do the logarithmic derivative, we would get L prime s chi over L s chi. And now when we take the logarithmic derivative, doing algebra very similar to what we had before, we get minus the sum over p sum over k, I think log p chi of p to the minus as, I think. And something like that. And then we could start doing the contour integrals as before. Up to minor algebra issue. I don't really care. It's going to be something of this form, and then we can do contour integration and then attack things as before. We would then multiply by like an x to the s over s, and we would argue as before. Unfortunately, if we're going to do this, what will we need to know?
Where the poles or zeros are.
Where the poles and zeros are. So we'll need a more detailed analysis of these L functions. And so the goal is not to go through things at this level. This is what we need if we want to get the result that the number of primes in arithmetic progression is a fixed multiple of x over log x, if we count up to x. So it turns out that to first order, the primes fall evenly in arithmetic progressions. To second order, there are biases. But to first order, you have phi of m possibilities. Each one gets 1 over phi m of the possibilities. The goal, one of the most basic questions you can ask in mathematics is, does it exist? Is there one of them? So if I'm just trying to prove that a prime exists that's congruent to A mod m, I don't care about, do they have the same number to first order? I don't care about what's the growth rate as x tends to infinity. I just want to know, if I go high enough, will I find one? This is overkill. It's nice, it's doable, but it's overkill. We don't need it. So it's gone. We will just focus on something like this. And then here's the great idea. Let's multiply by chi of A. Actually, by chi bar of A. And now we'll get chi bar of A log ls chi, and then leave a little space, is the sum over p, the sum k goes from 1 to infinity, chi bar of A, chi of p over k p to the ks. What should we do now?
Convert that into a sum over chi.
So now we sum over chi. And the reason we want to sum over chi is we want to use our orthogonality relations. And that's going to detect things here. So now, if we sum over chi mod m and divide by the number of such characters, well, we can pass we'll be able to pass this sum through the sum over the primes, through the sum over k, directly into here. The way you can really do this is you can split it up into, p coming from k equals 1, do things with finite, be very careful, look at convergence. And then what you'll see is if p is congruent to A mod m, chi bar of A, chi of p. Well, chi bar of A is the complex conjugate of A, of chi of A.
So you got 1.
So basically, if p is congruent to A mod m, these are multiplicative inverses of each other, their product is 1, and the sum reduces to the sum over p, the sum over k goes from 1 to infinity. P to the k is congruent to A mod m. And then we'll have 1 over k p to the ks, up to some small algebra mistakes. I might have made a mistake when k equals 2. I might have dropped, over here, maybe that should be chi of p to the k coming in. Might just be p congruent to A mod m. The main thing here is if you take s to be real, this is going to be a real number, it's going to be a non-negative number. If this number is not 0, what do you know?
That the total sum is infinite.
That the total sum is infinite. So all we need is to show that this sum is positive, and we win. And that's going to be the goal in Wednesday's class, is to go through and prove that this sum is positive. So if greater than 0, there exists a p congruent to a mod n. And we're not going to need to know nearly as much to be able to do that. Okay, so this is a good place to stop.